In this module, we are going to be considering Cartesian and polar coordinates. As we move beyond one-dimensional motion, we must consider coordinate systems. These are systematic ways of labeling the locations of points, and there are more possible coordinate systems than you have the desire to imagine. But these are necessary things because we need them to set a frame of reference within which we can specify things like position and velocity and so forth. Fortunately, we'll only need to deal with two basic coordinate systems in our class. But you will need to become very comfortable using these two coordinate systems. Doing so is going to require you to make considerable use of trigonometry. First, let's consider Cartesian coordinates. These are the simplest example of a coordinate system. They are composed of two sets of infinitely long straight lines, with the members of each set parallel to each other, and the lines from different sets are orthogonal or perpendicular to each other. For example, in the figure shown, the vertical red lines form one set of parallel lines, and the horizontal blue lines the other set, and the red and blue lines are orthogonal. In this example, the red lines might represent lines of constant x-coordinate increasing to the right, and the blue lines might represent the constant y-coordinates increasing up towards the top of the page. The x-axis extends in the direction of increasing x and is parallel to the lines of constant y, whereas the y-axis extends in the direction of increasing y and is parallel to the lines of constant x. The location of a point is given by a coordinate pair. For example, P1 is the point with x-coordinate 2 and y-coordinate 7, and here are a couple of additional example points. With Cartesian coordinates, the shortest distance between 2 points can be determined by the Pythagorean theorem. So, for example, if we consider the distance between the first and the second points, what we have to do is we take the difference of the x locations, square that, take the difference in the y positions, square that, and add those up and take the square root. And if we include the dimensions which we're going to assume are in meters, we get the following result. Of course, we can do the same thing between other points. Now, a Cartesian coordinate system is not required to have its axes horizontal and vertical. We can rotate them. This can be especially useful if we're thinking about problems like an inclined plane where we want to measure positions parallel and perpendicular to the incline. Another useful set of coordinates have one set of constant coordinate lines defined as concentric circles. The red lines are lines of constant radius r beginning at the central point called the origin. Beginning at the origin are also radial lines of constant angle theta. The blue lines are orthogonal to the red lines everywhere they intersect. The r theta coordinates are known as polar coordinates. Radial lines of constant angle can be measured in degrees, as shown in the figure, or in radians. Let's remember that 360 degrees is equal to 2 pi radians. A theta axis is rarely drawn in such figures, but a radial axis is sometimes drawn along the line of constant theta equals 0. The location of a point is given by, again, a coordinate pair, r theta, in this case 12 and 60 degrees. And here's another example. With polar coordinates, the shortest distance between 2 points can be determined by the law of cosines, as given below. So, for example, for our 2 points, again, if radial coordinate is measured in meters, then we can just take the radial positions of the 2 points, their angles, plug them into the formula, and simplify to get the result that is shown in the diagram. While using the law of cosines to determine the distance in polar coordinates is straightforward, few students remember this rule. More importantly, we will frequently need the skill of converting between polar and Cartesian coordinates. This skill will become very important soon when we learn to add vectors in 2 dimensions. But for now, it will give us another way of finding the distance between 2 points in polar coordinates. The approach is very straightforward. We start by simply aligning the origin of a Cartesian coordinate system with the origin of a polar coordinate system. Next, we want to simplify the picture just a little bit, and we're going to turn the line of constant angle through the point into a hypotenuse of a right triangle. Given this picture, we can now see that the x-coordinate of the point is going to be given by r cosine theta, and the y-coordinate of a point by r sine theta. Converting between polar and Cartesian coordinates turns out to be rather simple. We just need to use the Pythagorean theorem and a little bit of trigonometry. So for example, if we have the x and y coordinates in Cartesian coordinates, we can find the radius of the point in polar coordinates using the Pythagorean theorem, and we can find the angle theta using some trigonometry in terms of the tangent function. Or if we're given the radius and angle, we can easily calculate the x and the y coordinates again using some trigonometry. And just to remind you of a few useful identities, here are the values of sine theta and cosine theta for a few common angles. Now, in order to find the actual angle theta given some polar coordinates x and y, involves taking the inverse of a trigonometric function. It's important to remember that these inverse trigonometric functions may not give you the answers you expect if the Cartesian points xy that you're converting is not in the first quadrant of the Cartesian coordinate system. The answers you get from these trigonometric functions measured counterclockwise from the positive x-axis will always be in the range of minus 90 degrees to 180 degrees. Let's investigate this a little bit more carefully and make sure everybody remembers how these things work. So, let's consider first simply plugging in the Cartesian coordinate numbers using the actual values including their signs. So, in the first quadrant, the x and y coordinates have both positive signs, and the angles returned by the inverse trigonometric functions are in the range 0 to 90 degrees. Now, in what we're going to do here, we're going to write everything down in such a way that the answers we get are between 0 and 360 degrees. Now, if we go to the second quadrant, of course, the x-coordinate is now negative. And if we plug the quantities x and y into our inverse trigonometric functions and simply take the result that comes out, it's not always going to be the right answer. The equations in red show the results from the inverse trig functions as they must be modified in order to give the correct value of theta between the range 0 and 360 degrees. Notice that the inverse sine and the inverse tangent have to be modified. We have to take the results and either subtract or add that to 180 degrees. In quadrant 3, well, all three of the different inverse functions give us the wrong answer because both x and y are negative numbers. And in quadrant 4, well, it gets a little bit odder still because in this case, two of the functions, the sine and the tangent, if we plug in x and y with the correct sign, will give us a correct answer, but it's actually returning a negative answer between 0 and minus 90 degrees. And if we want the answer to be between 0 and 360 degrees, then we have to add 360 degrees to what's returned. And the cosine still returns the wrong answer. Now, the equations in quadrants 3 and 4 can actually be modified in such a way that they give an answer between minus 180 degrees and 0. And this gives them in a somewhat simpler form. All right. So if we do this, then the equations as shown will actually give us answers between minus 180 degrees and 180 degrees. This is a little bit simpler, but you have to remember that we're using both positive and negative values for the angles. Now, another approach for looking at for using the inverse trigonometric functions is to use only the magnitudes of the x and y Cartesian coordinates. This changes nothing in the first quadrant. In the second quadrant, well, we still have to modify things, but we modify things in a more uniform way. Now we simply take the value from the inverse trigonometric function and subtract that from 180 degrees. In quadrant 3, again, it's more uniform. We take the result from the inverse trigonometric function and add that to minus 180 degrees. And in quadrant 4, we simply take the negative of the result returned by the inverse trigonometric functions. In this approach, the inverse trigonometric functions all return the smallest angle with either the positive or the negative x-axis. Then in quadrant 2, we simply subtract this angle from 180 degrees. In quadrant 3, we subtract 180 degrees from the angle, and in quadrant 4, we simply take the negative of this angle. This is probably the easiest way to remember how to use the inverse trigonometric functions.